Hello. So to calculate ECSA from CV curves, we need to know once you have the CV curves at different scan rates, let's say for our material, from the y-axis we have current. So let's say for 5 millivolts per second, we have these two numbers at OCP, which is 0 volts. So we need to get these two currents, the lower one and the upper one, and take the average of that current for 5 millivolts. Then for 50 millivolts, we need to take the peaks of these currents and average, then the peaks of these currents and average. Let's say 5 millivolts, we get around minus 1 milliamps and minus 1.2 milliamps, and our average current will be 1.1 milliamps. So what we'll do, we'll plot scan rate on the x-axis. So 5 millivolts per second, we get around minus 1.2. It should be the absolute current, so we need to take absolute numbers. So 5 millivolts per second on the x-axis and 1.1 milliamps on the y-axis. And what happens is that as the scan rate increases, the values of current on y-axis also increase. We can discuss the reason for this as well, but what you will do is 5, 50, 100 or all of them, and plot them like this, and you'll get a straight line for the data points that you have. So now that you have x-axis and y-axis, you can just take the slope from the linear region. How the slope will look like? Slope will be on the x-axis, since you have y2 minus y1, x2 minus x1. So what you will be getting is millivolts. What you will be getting is amps per meter square on the y-axis divided by millivolts per second on the x-axis. So if you rearrange this term, you can actually get this term into ampere second over voltage or millivolts. So you can rearrange this term to get this number, and once you have ampere second divided by voltage, ampere second is charge and voltage is V, and this is how you get the capacitance. So normally the units for this should be millifarads per square centimeters, and in this way you can plot capacitance of different materials. Let's say you have a different cobalt nickel compositions, which you can label here, and capacitances of this, and the best capacitance should ideally give best HER performance. For the HER performance, you can just plot the LSV like these. Let's say this is the one, this is the second one, this is the third one, and the limit is current density, how much voltage it takes to reach 300 milliamps of current density. Voltage required to reach 300 amps per square meters of current density. So this is what you need to show with LSV, and ideally the surface area and LSV results should match. Ideally, the higher the surface area, the better the HER performance. Hopefully you can able to understand and do it now.